In this video, we're going to look at two different types of sensors. Silicon IC sort of sensors that use an integrated circuit, and we'll look at thermistors as well. So these first ones, the integrated circuit style temperature sensors. Essentially, when we say IC, we're talking about integrated circuit. That's what it stands for. Basically how they work, they've got one or two diodes or maybe transistors in there, configured in a diode mode. And they're designed in silicon, so you can have a wafer of them. You can have thousands of these that you cut out and you put in a little integrated circuit. Now, there's a current source that's supplied to this transistor or diode. And we know that if we're supplying a current source to something, we can then measure the voltage across that. And that voltage will be dependent on the amount of temperature that device experiences. So when we measure the voltage across that semiconductor device, we can use that to infer and calculate what our temperature is. Now, there's different types of these IC temperature sensors. Ones up above, like the LM35, was a very popular one for many years, mostly been replaced now by temperature sensors that have wider ranges and better measurement capabilities. Some of these will have analog outputs where we connect them up to an analog to digital converter, and we read in the analog voltage from these and it will tell us what temperature it is. Some of them will have digital outputs where we connect it to a microcontroller and it will actually just send out whatever quantized value it has. They've essentially got an analog to digital converter inside them. They've done that measurement and they're sending it out. Now, these can be quite accurate. These LM35s are accurate to about 10 millivolts per degree Celsius. So there's pros and cons associated with these IC temperature sensors. One of the big pros is they're linear, which means as the temperature increases, the output of the sensor increases in a nice linear way. They're also quite low cost and quite small, and often we can solder them to a small circuit board or something like that. So for mounting them, we've got a fairly ready way that we can actually mount them, which is great for some applications. They're also quite low power, something in the order of 60 microamps, which is, for many applications, a very small amount of power. They do have some drawbacks though. So the range of these is somewhat limited, minus 50 to 150 degrees. Now you might think, well, that's a huge range. It's more range than my body will ever experience. And you'd be right. But when we look at some of the other sensors and we start seeing very, very wide temperature ranges through to the very cold cryogenic areas, through to the very hot furnaces, we realize that some sensors we need to be much, much hotter than this or much, much colder than this. These sensors are a little bit lower in accuracy than some of the other sensors, and they can be a bit slow to respond. They might take a second or a few seconds to heat up or cool down as the thermal mass of the piece of silicon, the integrated circuit, heats up or cools down. We also do need a power source associated with them, which we don't need with all our different. Now, there's heaps of application areas where we use these sort of IC temperature sensors, from computers and mobile phones, making sure our phone isn't overheating or something like that, being integrated into battery packs to make sure battery packs aren't overheating, medical devices, patient monitoring, all sorts of different areas to use this low cost and easy to interface temperature sensor. Okay, now we'll move on to thermistors. Now, thermistors are essentially temperature dependent resistors. So a resistor that the resistance of that sensor changes with temperature. Now, these aren't new. The IC temperature sensors we looked at before, they're relatively new, the last few decades or so. But these thermistors, well, the basic principle's been around for a couple of hundred years almost. Michael Faraday, a very famous engineer and scientist, discovered this behavior, this resistance changing with temperature with silver sulfide. Now, basically, we have some different metal oxides which form semiconductors, and we can have various polymers as well. And some of the materials I've got listed there, things like chromium and cobalt and iron, manganese, nickel. And we have two main types of these. We have the NTCs and the PTCs. The NTCs are the negative temperature coefficient thermistors. Now, these are by far more common, much cheaper and easier to fabricate. But basically what they mean, as temperature increases, the resistance decreases. The PTCs are the opposite. So as temperature increases, resistance increases. And this makes them very popular for some applications like thermal fuses, for example, where rather than having a traditional fuse, we could have a fuse that when there's too much current flowing through that fuse, it starts to heat up And as it starts to heat up, rather than blowing like a normal fuse does and cutting the connection, the resistance of it increases. And when the resistance increases, it allows less current to flow through and avoids having to replace a fuse, because what we can do is we can let the system cool down, fix whatever's wrong, and then once the thermistors cool down again, it will conduct current well through it again. Now you can see here a whole lot of different types and configurations of these thermistors, from small ones that can be soldered onto circuit boards through the ones on wire leads and things as well. Now these thermistors are very sensitive to temperature changes. You can have thermistors that the output will change by up to 10% per degree Celsius, which is a fairly big swing. Now the typical response time is half a second to 5 seconds, so fairly slow, and in the sort of response time for the IC temperature sensors that we just talked about previously. Having said that, these have a wider operating range, particularly in the positive sense than those IC temperature sensors. They can get approximately twice as hot. Remember I said these are resistors, they're thermal resistors. We have here one of the typical ways we can calculate that thermal resistance based on resistance at a standard temperature, like 25 degrees Celsius, like a standard temperature and pressure sort of arrangement. Beta, which is a material constant value that we can read on the data sheet of the device. And the actual temperature that this thermistor has been heated to or cooled to in degrees Celsius. So if we've got those different parameters, we can calculate what the resistance will be, and we can go back in the opposite direction and work out what the temperature will be based on a particular measured resistance of the thermistor. So we have some pros and cons with thermistors. They are quite accurate, they are quite low cost, and they are quite reliable and robust as well. Having said that, they can drift a little bit over time. They can suffer from self-heating, and if we've got current running through this thermistor, it can heat it up a very small amount depending on how much current we're using through there. And that will heat it up rather than the environment heating it up. And they are quite non-linear, which is what we'd expect from that E term that we had in the previous slide. Now, thermistors have lots of applications, from being fuse replacements, particularly for those PTC, the positive temperature coefficient ones, through using them in ovens and fridges and digital thermometers, for example.